Sampling represents one of the more technical topics we'll be studying in this course. This video is considerably longer than our prior videos because we are going to be tackling three core issues. What is sampling? How is sampling used to test internal controls? And how is sampling used to test accounts? There are a lot of different ways to sample. In this course, we're not going to cover them all. We're going to be focusing on two types in particular: attribute sampling and monetary unit sampling. We don't study the classical variable sampling that you would have taken in a statistics class, block sampling, systematic sampling, or things like that. One of the first terms we need to make sure we understand is called the representativeness of our sample. We want a representative sample. And so representative of the population. Remember, whenever we're doing sampling, we're trying to reach conclusions about the population, not the sample. The sample will know 100% certain what the results we get. We're going to try and make inferences about the population. So we'll see the green bar here. The sample is randomly taken across the entire period, where the second one isn't really representative because they're clustered all at one period. Now, intuitively, we look at this and say, that's absolutely not a representative sample. But statistically, it's a possible sample. So that the pink bar is just as likely at random of being picked as the green one. So what I mean by that is we tend to think things that are unusual are impossible. And so humans can't actually draw a random sample. You have to use computers to do that. Now, if I was doing testing here, if I was concerned with these transactions at the end, I would actually redefine my population to be anything in this last quarter and sample from there. So some general principles you need to make sure you understand about sampling. The more confident we need to be in our conclusion, the larger the sample. And confidence is also related to sampling risk. And so if I said you want to be 95% confident, that's willing to say there's a 5% chance you're going to get unlucky and what your sample reveals will not actually be right. So compared to 95 versus 90, and those are usually the 2% we focus on. If we go from 95 to 90, we'll need a much smaller sample. If we want to increase our confidence from 90 to 95, we're going to have to increase our sample size. The more of an error we can tolerate, the smaller the sample we need. So for example, if I want to reach a conclusion within plus or minus 1%, I need to be very precise. I need a very large sample to reach that conclusion. But if I said, as long as it's within plus or minus 5% or 10%, I can use a much smaller sample. On a related note, the expected errors or the expected number of flaws is going to cause me to increase my sample size. And that relates to the concept of precision. Precision is how much wiggle room do we have when we do an audit. The more precise our testing needs to be, the larger the sample size we need. So if we increase sample size or increase tolerable deviation rate or expected deviation rate, we're going to narrow our precision. As we narrow our precision, we need to increase our sample size. Now, I do want to note for you that in our discussion, we haven't talked about population. It's because for the most part, most of our audit tests deal with larger populations, and therefore it doesn't seem to be a relevant factor. Small samples, it would be relevant, but once you get above 500 items, it doesn't really matter that much. I would even argue above 250, that you're not going to see much movement, but as this chart indicates, there's virtually no movement once you get over 1,000. Now, there are four general types of errors we can make. Two fall within statistical problems, two fall in non-statistical. A statistical problem would be a false problem, false positive. This is where we conclude there is a problem when there in fact is not a problem. This means we're going to do additional testing. This is a measure of an inefficient audit. A false negative means we say there are no problems when in fact there are problems. This will undermine the effectiveness of our audit. Within the non-statistical world, if we misclassify errors as non-errors, that's going to undermine the quality of our data. If our data is flawed, our conclusions are going to be flawed. The other possibility is we actually picked the wrong procedure. So the procedure which got us the data which fed into the statistical modeling was flawed, that will also undermine the confidence of our process. So, but we're always going to be not limited to the computer, because we'll do a lot with computers. We're going to see humans are involved, which means there's going to be human error. Oftentimes it requires R to look at things and make judgments. And so even generating the data is a judgment task. And sometimes we'll have to get this evidence from third parties, and we'll have timing issues and delays and other issues. So what happens if you find a problem? And that's going to happen in any audit. You're going to find a problem. Well, the first option is you can increase your sample size. Sometimes the reason why we conclude there's a problem is we have very limited evidence. So we can increase the extent of our testing. The second option we can do is we can tell the client to fix the known errors to get us below materiality, or other things like that. We can wait for other tests to be completed. It may be that this isn't that significant. We might have a compensating control. We might have alternative evidence which speaks to this. And therefore, even though this test indicated there's a problem, we might find something that provides greater clarity. Another option we can do is increase other testing. No, I'm not saying we were testing for existence. We couldn't find that, so we're going to do more testing for completeness. I'm saying we might be able to do other testing relevant to this assertion. We could have the client go back and do additional testing, or our thermonuclear option, we could simply refuse to give an unqualified opinion, or we could issue a material weakness opinion if it's about internal controls. That option is theoretical. Very seldom would you want to reach that point because it's going to strain the auditor-client relationship. Now, there's two types of sampling. Non-statistical, sometimes called haphazard sampling. The other type is called statistical sampling. One is based on scientific principles, the other is based on auditor judgment. Both are used in practice quite a bit. There's not one intrinsically better than the other. Statistical sampling lets us quantify that sampling risk. It is a significant advantage. Non-statistical, we rely on the auditor's judgment. The advantage of non-statistical is the auditor can use their judgment to identify higher risk items. So it could conceivably be higher efficiencies, possibly even more effective. The problem is you can't prove it. It's a matter of opinion. And so it's subject to greater scrutiny. The PCAOB has identified sampling as an area of concern for the last decade for this very reason, that a lot of auditors tend to default more to non-statistical for inappropriate reasons. So for example, if statistical sampling said you needed a sample of 200, you use non-statistical judgment and say, no, I'm just going to pick the 100 most representative. That's not good logic, because your objective isn't to get a better test result, it's to lower cost. So how does this work? Comparing each other in judgment or non-statistical sampling or haphazard sampling, you're going to use your judgment to pick an item. You're going to use your judgment to pick to find the sample size, and your judgment pick a representative sample. You're going to apply the audit procedures, and you're going to use your judgment to evaluate the results. Statistically, what we'll do is we'll explicitly estimate certain numbers, the tolerable rates, the expected rates, and we'll use these numbers and mathematical principles to identify an appropriate sample size. Then we will use statistical methodology to identify a randomly selected representative sample. We'll apply our procedures, and we'll also use our judgment to interpret the results based on scientific principles. Unfortunately, what happens sometimes is the auditors will do the first 3 steps in judgmental and then attempt to interpret the results with statistical, which is one of the concerns the PCAOB has raised. So why use statistical statistical sampling should, in theory, give you the most efficient sample. It will also let you measure how sufficient your evidence is, and it lets you quantify the sampling risk. However, it does require training. If it's not well trained, you're going to see inconsistent applications. And oftentimes you do wind up with larger samples, which makes it more costly to apply. However, concerning to me is this actual explanation. As a profession, I'm a little uncomfortable saying we don't do statistical sampling because we need to be trained and it's costly. If it's the better method, it's the one we should use. Another embedded reason this is we need to require reviewers to be equipped in statistical training. However, most auditors get their most extensive training in statistical sampling in the master's in accounting programs and in graduate studies. However, once you leave, you don't use this skill for a few years, then you're expected to review other people's work. You can't, so you encourage your subordinates to do non-statistical sampling, and it's a cycle where no one gets the expertise because no one is mentored to use it. Why do you think firms don't exclusively use statistical sampling? It's costly. They're not trained to do it. When is a population heterogeneous? What sampling technique is best? So we'll see the phrase homogeneous and heterogeneous. Homogeneous means that the population is uniform across. Heterogeneous means that we've got certain parts of the population have different traits. And that's where we're going to do a technique called stratified sampling. If you remember back from geology or science in high school, the Earth has many different stratas or layers. You're going to define each several populations and sample each population with different, as if it were its own unique population. If $100 use sampling, what are the odds they reach the same conclusion? It depends on the confidence level. If we have a 95% confidence level, $100 do a test, then it's 95% of the time they should get the same results. However, if $100 use non-statistical sampling, we have no idea what are the odds. That's the disadvantage of non-statistical, is maybe all 100 reach the same conclusion, maybe they reach 100 different conclusions. We don't know. Does the assertion tested influence? Yes, absolutely. We're going to design our test based around the assertions. We don't ever want to lose track of, we're going to be looking at accounts and assertions. So stratified versus completely random. A stratified sampling is where we're going to be defining parts of our populations. So we might, if we're auditing accounts receivable, we might say all small accounts, we're going to sample 1 out of every 1,000, but any account over 1 million, because they're in and of themselves material, we're going to audit them with 50% sampling. And so you can set different tiers based on the risk. Reliance on technology for professional judgment. You cannot say the computer told me. You always have to use your judgment to interpret the results. You always are up to you to accept responsibility for the outcome. You cannot say the computer told me. Automated controls means we generally need to do less testing. If a control is systematically designed and we understand the underlying computer code, then as long as we verified it worked in the typical scenario and some atypical scenarios like exception testing, then we're going to be able to be much more efficient. So how do you do attribute sampling? Well, let's just first define what attribute sampling is. Attribute is when we're looking at a yes/no question. Does a control work? Yes, no. It's sometimes called binary testing, Boolean testing, all these types of phrases where it either works or it doesn't work. And so we're going to be looking at what percent of the population has this trait. So it is a type of statistical test. We're going to estimate the proportion of the population that possesses a specified trait. The most common use is for test of controls. So we're going to say a control works as long as it doesn't fail more than 7% of the time. And so from that, we're going to do an analysis. And so first thing we need to do is identify our objective. We're verifying that a control prevents unauthorized users, that payroll checks are not sent without 2 signatures. In order to do this, we're going to have to define our sampling population. So what is the actual population we're trying to study? Is it transactions? Is it forms? Is it this? Then we're going to define the sampling unit. What is the particular item we're going to be testing? And then we need to define the control deviation. It's very important you define the control deviation before you begin. If an item is missing, is that a deviation, or is that something that needs to be redrawn? And so depending on what the test you do, you'll have different responses. Generally, for example, a missing form is considered defective. But one that's been voided is not defective and would be replaced. So, for example, if the client can't produce evidence that something was properly authorized, the form is missing, we're going to assume that the control didn't work. But if we select an item and the client voided it because there was a date problem, that the client didn't do anything wrong. That just wasn't in our true population of valid forms. So we're going to come up with some figures, and we're going to, what's their desired confidence level? Again, most of the time that's going to be 95% or 90%. Our tolerable deviation rate is going to depend on how much we plan on relying on the control. And our expected deviation rate will be based on past experience with the client, our own observations, our judgment. Note, tolerable deviation rate and expected deviation rate are the auditor's judgment-based assessments. So the more you plan, the more critical control, the less you can tolerate deviations. And it'll depend on your control risk. So then we'll select our items. We'll use a random number selection, or we could use a systematic. That's where we do a step approach. We pick a random starting point, and then we go every fixed interval. So we use Excel to generate a number between 1 and 100. It says 92, and then we take every 100th item after that. And so that's a great technique. It's relatively simple to implement. The only flaw would be is if the client has a systematic fraud, we wouldn't be able to get it. So we need to make sure we don't select voided items. We want to have look at unused or inapplicable documents. We want to, if the client won't provide a document, so it exists, but they won't provide it, that's a problem. Why would we stop the test before we're completing? If we've said we can only tolerate 6 errors and we find 7, we don't need to continue testing. Then we're going to calculate our sample deviation rate. So if I looked at 100 items, I found 5, my sample deviation rate is 5%. But I also need some sampling allowance. Sampling allowance is the what if I'm wrong. And so you've seen this in presidential election polls where candidate A has 42% of the population supporting them, plus or minus 5%. That plus or minus 5% is the sampling allowance. We generally are not worried that a control is the lower end. We generally are concerned only about the upper end. And then we're going to reach some conclusions based on what we find. So there are 3 basic outcomes that could happen. Our results indicate the control is reliable, and it is reliable. We've reached the correct conclusion. Second possibility, our test results indicate it does not work, and it actually doesn't work. We've reached the correct conclusion. Now, the errors are of varying significance. If we say that the control does work, but it is in fact unreliable, we've accepted what the client has said is true when we shouldn't have. We've been ineffective in our job of providing a correct audit opinion. The alternative is we say the control doesn't work when in fact it does. This is what is going to undermine the efficiency of the audit, because we're going to have to either increase our sample size, do additional testing, work with the client to provide alternative evidence. Generally speaking, the client will let us know they think the control works, and they're going to push for us to resolve this issue. Or we're going to have to do additional testing. However, if we said the control worked and it didn't, the client's not going to come to us and notify us that we've made a mistake. I think an example would be helpful to illustrate this. So 95% confidence level, 6% tolerable deviation rate, 1% expected population deviation rate. Now, you don't mathematically do anything at this moment. It's what we need to do is go to tables or use a software package to do this. In the data analytics class you're going to take in the MAC program, or as you study for the work with firms, they will have packages. ACL or IDEA will be the 2 most common ones you're going to see in practice. But in theory, you could even generate this from Excel. We normally rely upon the AICPA provided tables in examples, because that way we're not having to rely on technology. I expect in the next few years that will change as Excel becomes more common, but we're not there yet. So here's where we're at. We'll be given a table. Along the top will be typically the tolerable deviation rate, and along the rows will be expected population deviation rate. So some general observations first. As the tolerable deviation rate increases, our sample size decreases. That makes sense. The more errors we can tolerate, the less evidence we need. As our expected deviation rate increases while keeping the same tolerable deviation rate, our sample size increases. Now, some of these are blank. It's because there's no scenario where that would make sense to do that test. It would be an astronomically large test. And there's some scenarios that make sense. For example, if I told you you expected a population deviation rate of 2% and a tolerable of 2%, it would just be you would need to sample the entire population because there wouldn't be a scenario where you could have, it would make sense. And so in this scenario, we were given 6% and 1%, we find this. And so you'll see this on CPA test questions. And I'll post a few workout problems for you to practice this yourself. But this table will always be given to you. So we'll be given a large population and we'll have to pick a starting point and we'll go through. And so we've got our invoice numbers and we'll pull these up. And in this example, they told us, hey, you found 2 problems. So we looked at 78 items and we found 2 problems. So 2 divided by 78 gives us 2.6%. And our computed upper deviation rate is 8.2%. Well, where did that come? Again, it's going to be an AICPA provided table. So we'll look at our actual number of deviations and we'll have to go to a sample size. And so generally speaking, you go down the number of rows. No, we didn't pick 80 because if you look here, as you go down the column, the number gets smaller. So we're going to pick the row that's closest to what we're looking at, but not greater than. So even if it had been 79, we would have gone to 6.2. Now you can make an 8.2 and not 7.7 because we'd rather be biased in favor of being effective than efficient. Now you could try an extrapolation technique if you felt that was helpful, but generally speaking, if you're getting that close that it's going to matter, that's not going to work. So in this case, one could say our sample deviation rate was 2.6%. It would be a fair question, what's the sampling allowance? Well, that would be 8.2 minus 2.6 or 5.6. Now again, just think about that for a second. We found 2 errors, and based on finding 2 errors, we're saying we're 95% confident that there's 8.2% deviation rate in the population. And so if we could only tolerate 6% errors, we're going to conclude that there's a problem because we're above our tolerable rate. Now, so what would be my options at this stage? Well, just look at what happens if I can increase my sample size. If I double my sample size, even if I find more items, I will have a lower rate, I'll have other benefits. And so, because we see this falls as we go down. So we would not rely on that control. So what would our options be? The first is expand our sample. The larger the sample, the lower the sampling allowance is going to be. We could just assess the control risk as higher, which is going to necessitate that we do additional substantive testing. If you remember the audit risk model, AR equals IR times CR times DR. If CR goes up, then DR has to go down. The only way to adjust DR is to change the nature, extent, and testing of our problems. And we would need to conclude whether, for at least for a public company, whether a material weakness or significant deficiency has been identified. A private company, we would need to work with the audit committee, depending on what they had contracted us to do. Now, if we were doing this with non-statistical sampling, we'd look at the rules. Rules of thumb. Again, these are rules of thumb. You could do whatever you want because it's judgmental. We would use whatever method we wanted, as long as we didn't do it in a biased way. We calculate the sample deviation rate, and then we'd say whether we think that's high enough. to warrant a problem. And so when we look at accounts, so think accounts receivables, the one we primarily think about, we do a technique called monetary unit sampling.